Eutrophication is the process of oxygen and sunlight depletion from water bodies while they get over-enriched with nutrients and minerals. Usually, eutrophicated areas are originated by poor domestic wastewater management, industrial waste, and flooding debris. More and more water bodies around the world are passing through this process due to the urban sprawl. Flooding weeds find suitable conditions to overgrow in eutrophicated zones, mostly with calm water and little airflow. Dogweed, watermill, water hyacinth, sargassum are some species of invasive flooding weeds that are manageable in small water bodies. However, the removal becomes challenging in longer water bodies such as lagoons, bays, lakes, and dams. A water body plagued with flooding weeds can lose biodiversity and can gain great proportions of sludge, which in turn affect the sustenance of neighboring communities that need the water body for consumption, fishing, or recreation. In this research, we propose the development of a low-cost unmanned surface vehicle, a USV, for the monitoring and removal of duckweed from Lake Titicaca, a water body with frequent duckweed blooms that have caused financial losses and biodiversity decay. With this goal, we implement and deploy a steering angle estimation system to process RGB and stereo vision data coming from an OGD camera in real time to collect duckweed colonies and avoid collisions. The mechanical design of our device consists of two floaters that are joined with a central structure. This serves as a support structure for a superior case where we save the electronic components of the device. Each floater has a DC motor embedded within a fin located at the bottom. The device has a removable rack in the front to avoid garbage like plastic and only let pass ductwork. Moreover, each floater has a compartment to house a battery and proper connections to provide the USB with energy for movement. To collect duckweed, we included a net on the back that captures leaves once they pass through the central entrance. The central case consists of an OACD camera, a Jetson Nano development card, a Raspberry Pi Pico, an XP communication module, a GPS module, an H-bridge driver, and a voltage regulator. The final CAD design is a result of sketching and prototyping multiple times to ensure endurance and navigability for the USB. We printed the components with PLA and assembled them with bolts and epoxy glue, among other materials. The proposed design let us improve the device modularly. Once we developed an initial version of the device, it was necessary for us to control manually the USB from short and long distances. Therefore, we prototyped a small and portable remote. For the USB's autonomous driving function, we propose a steering angle estimation system that comprehends a ductweed detection model and a steering angle classification module. For practical purposes, we use the acronyms SAE for the steering angle estimation system and SAC for the steering angle classification module. The main SAC's role is to provide collision avoidance to the USB. Each frame and depth data captured by the OACD camera is passed to the SAE system to define the best steering angle. In addition, we include a module to average the current estimated angles within 9 immediate previous angles, aiming to obtain a more stable navigation. Finally, we deploy the SAE system inside the NVIDIA Jetson Nano development card. We scrapped 4,341 images from Google Images and the Global Biodiversity Information Facility to develop the duckweed detection model. Not only did we automate this process using Selenium and Python, but make sure about their free copyright. We labeled the samples for object detection with RoboFlow and augmented them to obtain 10,000 samples. We experimented with two versions of YOLO, namely YOLO version 5 and YOLO version 8 and embedded the best model inside the BPO of the OACT camera. On the other hand, we approached collision avoidance by exploring end-to-end learning and stereo vision. The first approach was named M3 and required to collect a dataset for deep learning. Given the challenges to collect data in situ, we developed a bespoke simulator and obtained 37,846 images that resembled the environment in Lake Titicaca. On the left, we can see the initial dataset characteristics, which were then processed to obtain a dataset of 49,000 samples, 7,000 for each of 7 categories, where 0 depicted movement to the left and 6 was movement to the right. What follows is the simulator developed using Unity and Blender that helped us to apply domain adaptation to the task of end-to-end steering angle classification. We also explored collision avoidance using stereo vision, which we later named as M4. This was possible given that the OACT camera used in the project provides depth information with high precision. Our experimental results let us obtain YOLO version 8S as the best duckweed detection model. Moreover, we contrasted M3 and M4 self-driving modalities, from which stereo vision-based collision avoidance obtained better results when testing the algorithm for duckweed removal inside the simulator. The USB proposed in the investigation has been successfully implemented with the required hardware and software features to collect duckweed. We performed tests in controlled and real scenarios to evaluate the navigability and endurance of the device. To test the SAE system, we simulated a real environment and performed multiple duckweed removal tasks with and without obstacles. We found out that stereo vision-based steering angle classification ended up being the best approach for the device.